Let's start our exploration of electricity, electrostatics, and magnetism by looking at what a magnet is and how magnets work. A magnet is material capable of attracting ferromagnetic materials and producing a magnetic field outside of itself. Now, this is a slightly more complicated answer than simply saying a magnet picks up metal or is attracted to metal, because that's not always the true statement. That's a pretty big misconception and misunderstanding about how magnets work. We'll talk more about what ferromagnetic means, but as far as a magnet is concerned, we need to know that there's two poles, a north pole and a south pole. If I take that magnet and I split it in half, it ends up creating two new magnets. Now, it doesn't give it a custom paint job, but the poles are the same. No magnet will ever have just a south or a north pole. Magnets themselves have the capability, based on their properties, to create magnetism. Magnetism is the attractive and repulsive forces that are caused by the motion of electrons in a magnetic field. Magnets have magnetic fields. Because of these fields, they either push away from each other or attract one another. Now, magnets attract and repel one another. North repels north, south repels south. North and south are attracted to one another. They stick together. As far as other objects, magnets only are attracted or pull up or magnetize materials made from iron, nickel, cobalt, or some alloys of rare earth metals, such as minerals such as lodestone. The key word here is iron. Notice that the iron is Fe. This is where we get the term ferromagnetic. So metal alloys such as steel, not stainless steel, but regular steel, that use iron are also magnetic. When you combine iron with other metals, you get alloys. So things like steel can also be attracted to magnets. This is why we see things like nails or paper clips as common magnetic items. These metals are ferromagnetic, which means they have some form of iron, nickel, or cobalt inside of them. Ferromagnetic materials can become temporary magnets. Notice the nail on the right side. I can connect paper clips through magnetism by clicking or linking them just to the edge. The magnetic force is extended from the magnet through the iron nail. Now, if I were to, for example, rub that magnet along the iron nail, I could create a temporary magnet from my permanent magnet. This would mean that some of those magnetic properties would continue to live within that iron nail and would act as a magnet. This is why sometimes you might see paper clips stick together. You may see sometimes silverware stick together. The driving force behind why magnets work is the magnetic fields. We're looking at a very specific particle here, an electron. Electrons are negatively charged, and traditionally you've seen them existing within an atom. Electrons travel from the North Pole to the South Pole. They always go in one direction, from north to south. As they travel, they create a path. The path that these electrons are following is our magnetic field. The direction that these electrons traveled determines the attraction and determines the poles of the magnet. Since electrons always leave the north and move to the south, those electrons are always moving away from north, always moving towards south. So if I know the direction or the field of my electrons, I can find the north and south poles of a magnet. If I were to bring another magnet in, let's try to link the south with the north. Look at the direction the electrons are moving in both of these magnets. They're both moving in the same direction. So that means that this magnet will attract. What we're actually doing when we connect two magnets like this is creating one giant magnet. So those electrons are not going to go from north to south, north to south. They'll go from the north end of one magnet and continue to the south side of the second magnet. Let's try a magnet that is north to north. In this case, the electrons are moving in opposite directions, from north away from north. This is why we get repulsion. They push away. Those forces push away. They don't push in the same direction. If you look at the lines created, or the path created by these electrons, the magnetic field lines are closer together at the poles. So as they're leaving the north and traveling to the south, they come together a lot closer than in the middle, where there's gaps in between the lines. This is why magnetic fields are strongest at the poles. You might be able to get attraction from the middle of a magnet, but the strongest ends are right on the poles, the north and the south. You may have heard the term North and South Pole when we talk about Earth. That's because the Earth is a giant magnet. We have a massive iron core in our planet, which creates a magnetic field. So we have electrons moving from the north and traveling to the South Pole. This creates a big magnetic field within the Earth, or around the Earth. This magnetic field explains how animals, such as birds, know how to traverse Earth, moving from north to south for the winter, for example. They're following magnetic fields. Humans don't have that capability necessarily, but we've learned how to harness magnetism in order to traverse Earth. We have compasses. A basic magnetic compass is designed to always point north. It does this because the red tip in our compass here is attracted to the north pole of the Earth. That's because inside of that compass is a tiny magnet. Now, we couldn't have the part that's actually pointing north be the north pole of a magnet, so inside of a compass we have a magnet that is aligned the opposite of the Earth. So the south pole of the magnet inside the compass is attracted to the north pole of the Earth. The north pole inside the compass magnet is attracted to the south pole of the Earth. This is why it automatically aligns north-south inside of your compass. Electromagnets are another way to create magnetism. Temporary magnet is created by moving a current around a ferromagnetic material, so in this case an iron nail. So we have the electrons travel through. They're moving in the same direction and they're traversing around the coil, which is around the ferromagnetic material. This will only work with something that has iron in it, since ferromagnetic materials can become temporary magnets. Going back to our definition of magnetism, magnetism is the attractive and repulsive forces caused by the motion of electrons in a magnetic field. This iron nail does not naturally give off electrons from the north and receive them in the south. What we need to do is create that motion of electrons. Whether it's naturally occurring or man-made, moving electrons around a ferromagnetic material creates a magnet. Just like a regular magnet, the north and south poles are going to be the strongest. Just like a permanent magnet, this creates magnetic fields. Electrons travel from the north to the south. Now I know that that end up top is the north because I know the flow of my electrons. Electrons move from the negative terminal of my battery to the positive. So they go, in this case, up my nail and then out the top. If they're going out the top, that means they're going through the North Pole down to the South Pole. So the top is north, bottom is south in this case. Magnetism and electricity are very strongly connected. A magnetic field can create an electrical current, which we'll explore as we move through this unit. An electrical current can induce a magnetic field. We've already seen that. We took an electrical current and we created an electromagnet. This concept of magnetism and electricity going hand in hand as they do is what creates electricity or generates electricity for us in many, many cases. This is also how basic motors work. If I can use magnetism and electricity, or I use magnetism to create electricity, I can use electricity to create magnetism and attract and repulse. Both involve the motion of electrons, so we need to start seeing electricity and magnetism as different ends of the same spectrum.